Good morning, students. Welcome back to Signals and System online video lecture series. We have been discussing the first unit, that is classifications and the definitions of signals and systems, in which the first topic is completed in the first unit. We have been discussing the second topic in the first unit, that is elementary continuous time signals. There are 5 elementary continuous time signals are there, in which we have discussed the first one, that is unit step signal, in the previous class. In this class I am going to talk about the remaining 4 elementary continuous time signal. Before going to talk the remaining 4 continuous time signals that are elementary continuous time signal, I am going to revise the classification of elementary continuous time signals. The first one is unit step signal, second one is a ramp signal, and the next one is about the impulse signal. Fourth one is exponential signal, in which again we will be having the 2 types. One is a real exponential signal, another one is complex exponential signal, and the last one is, that is fifth one, it is a sinusoidal signal. All these classifications I have given in the previous class. So not only classification of the continuous elementary signals, I also discussed one particular type of elementary continuous time signal, that is unit step signal. So here we have to discuss all the elementary signals in the continuous time only, but in the 4th unit the same things we have to discuss in the discrete time. So that I am going to discuss the unit step signal, or I am going to discuss the elementary continuous time signals as well as elementary discrete time signals in this unit only, so that in the first unit, if you are good at the first unit, around 50% of the 4th unit is also completed with the continuous time signals and the discrete time signals. The first important elementary signal, that is called unit step signal. Unit step signal is in general denoted with u of t if it is continuous time, and it can be denoted with u of t, and if it is a discrete time signal, it can be denoted with the u of n. We have studied this, what is n and what is t, in the comparison or the difference between the continuous time signals and the discrete time signals. We know that u of t, it is a continuous time signal, that is unit step continuous time signal. U of n, it is a unit step discrete time signal. In the last class I have given the mathematical representation of that continuous time signal, that is unit step signal, that is given as u of n is equals to u of t is equals to, it is 1 for t greater than or is equals to 0, 0 for t less than 0. It is a continuous time signal. By making use of this mathematical representation, we can easily draw the signal by using the graphical representation. In the last class I have explained how to draw the unit step signal that is in graphical representation, and this is about continuous unit step signal. And if you wanted to define the discrete time unit step signal, that is u of n is equals to here n is an integer value, that is may be positive integer or negative integer. U of n is equals to 1 for values n greater than or is equals to 0, otherwise 0 for n less than 0. This is I have given in the last class the main advantage or the main application of continuous time unit step signal, directly we will be giving the continuous force from the off state to on state to start a motor or to start a engine of any electrical device. That is the best example for the unit step signal. In the last class we have discussed this one. The next one I am going with the ramp signal. That ramp signal is denoted with the R of t. If it is continuous time ramp signal, that is denoted with R of t. If it is a discrete time ramp signal, it is denoted with the R of n, where t is a independent variable, that is time, and here n is also independent variable, that is an integer. So that I am going to define the ramp signal. But before going to define the ramp signal, we should know what is the necessity or what is the introduction about the ramp signal. Here, this ramp signal is linearly growing function for all the positive values of independent variable. Here the independent variable is t and n. For t and n values are, if the t and n values are positive, so that the signal will be linearly growing function. Signal will be linearly growing function. If t and n are negative, then that signal will be signal amplitude will be the 0. So that I am defining the ramp signal or the ramp function. It is a linearly growing function for positive values of independent variable. That means amplitude of the signal linearly increases as the positive values of independent variable increment. This type of signal is named as unit ramp signal, and the unit ramp signal and as well as unit ramp signal can be defined in the continuous time and as well as discrete time. In case of continuous time, it is denoted with R of t. In case of discrete time, it is denoted with R of n. So that I am going to represent this ramp signal using the mathematical representation. This is a ramp signal. Then I am going to define the ramp signal now. Ramp signal, we know that ramp signal is denoted with R of t. R of t, it is a continuous ramp signal whose amplitude is linearly increases for all the positive values of t, that is t is a independent variable. For a t is less than 0, whose amplitude is 0. This is about the mathematical representation or simply definition of continuous time. This is a definition of continuous time ramp signal. It is a definition of continuous time ramp signal or the ramp function. We can define the same ramp signal in case of discrete time, so that we know that discrete time is denoted with R of n. R nothing but it is a ramp, and ramp function is nothing but ramp signal which is linearly increasing, so that this value is n for n greater than or is equals to 0. For all the positive values of independent variable, that value is linearly increasing with respect to the independent variable. If the independent variable value is negative, then the amplitude of that particular signal will be 0. So by making use of this mathematical representation, we can easily draw the ramp signal. Now I am going to draw the ramp signal, that is continuous time ramp signal. I am going to draw now. Continuous time ramp signal. What is the definition of continuous time ramp signal? R of t is equals to t. This is R of t is nothing but t for t greater than or is equals to 0, 0 for t less than 0. It is the continuous time ramp signal. I am going to represent that signal is in uh, is in graphical representation. Then this is the x-axis, and then this will be x-axis. So this is y-axis and this will be x-axis. X-axis always used to represent the independent variable, this is t, and so that this is minus t. And y-axis always used to represent the amplitude of the signal, that is r of t, and this will be minus r of t. Then for all the positive value whose amplitude is 1, whose amplitude is t, so that here these are all the positive values of t greater than or is equals to 0. Now these values are t less than 0. If it is t less than 0 means it is minus value, minus t. It is t greater than or is equals to 0 means it is positive value. For example, I am going with the one particular analysis, that is here, for example, here t is equals to 0. T is equals to 0 means, if t is equals to 0 means r of 0 will be also 0, because we are simply replacing t by 0, so that it is 0. If I am going with the t is equals to 1, t is equals to 1 means I can get the t is equals to 1, r of 1 will be 1 only, so that I can get the amplitude is here. If r of 2, that means what, t is equals to 2 means this one, and the r of 2, that means r of 2 and t is 2, so that here amplitude is also 2, like that I can get the signals are linearly increasing with respect to the independent variable. So that signal will be like this. Now I can go with the signal. This is the signal here for all the positive values, and the signal is linearly increasing for t greater than or is equals to 0. This case is completed. Coming to this case, when t is less than 0, the amplitude of that particular signal will be 0, so that whatever may be the value of t, when that t is in negative manner, then that value of that signal amplitude is also 0. This type of signal is named as, it is a continuous time ramp signal. It is a continuous time ramp signal. Now I can go with the discrete time ramp signal. So now I am going with the discrete time ramp signal. This is discrete time ramp signal. You have to remember, the point is that ramp signal is nothing but it is a linearly increasing signal for all the positive values of independent variable. That independent variable may be t in case of continuous time, that independent variable is n in case of discrete time. So that I am defining the discrete time ramp signal, that is r of n is equals to, r stands for ramp and r of n. By seeing the n, we should understand that it is a discrete time and n is an integer. R of n is equals to n, for n greater than or is equals to 0, and r of n is equals to 0 for n less than 0. So that we can plot the discrete time ramp signal now. Discrete time ramp signal, I am taking the graphical representation to represent this particular signal. This is x-axis and this is y-axis. Always x-axis used to represent the independent variable. Here the independent variable is n, and if it is n, this will be the minus n, and this is x of n. Then n is what? N is integer, so that I am taking all the possible integer values of n. This is 0, this is 1, 2, 3, 4, 5, 6 and so on. Then here I can take minus 1, minus 2, minus 3, minus 4, minus 5. So this is what? It is 0, 1, 2, 3, 4, 5, 6. This is what it is: minus 1, minus 2, minus 3, minus 4, minus 5. For all the negative values, go with the second case. For all the negative values of n, whose amplitude is 0, so that we can represent that is in the form of like this. So that here the amplitude for all the negative values, this is what it is: n less than 0. That means what? N is negative now here. For n is negative, whose amplitude is 0. Amplitude is 0 at a discrete instant of time. And coming to the first case, r of n is equals to n for n greater than 0. Substitute n is equals to 0. R of 0 is equals to 0. That means what? At n is equals to 0, that amplitude is also 0. R of 1 is equals to 1. That means what? At n is equals to 1, whose amplitude is also 1. Whose amplitude is also 1. That n is equals to 2, whose amplitude is also 2. Then I can go with like this. This is 2. At n is equals to 3, then amplitude is also r of n is also 3. N is equals to 4, it is also 4. And n is equals to 5, and it is also 5. Like that, what? For all the positive values of n, n greater than is equals to 0. In the case of n greater than is equals to 0, greater than or is equals to 0, the amplitude is linearly increasing signal, and this type of signal is named as a ramp signal. It is a ramp signal. Now we have discussed the ramp signal in case of continuous time and as well as discrete time. In the last class we have discussed the unit step signal in the continuous time and the discrete time. Now we have discussed the ramp signal in continuous time as well as discrete time, and so that the two elementary continuous time signals are completed. First one is unit step, and it is defined in continuous time and as well as discrete time. In continuous time, u of t is equals to 1 for t greater than or is equals to 0, and it is 0 for a t less than 0. That is what? For all the positive values of independent variable, whose amplitude is 1. For all the values of independent variable is negative, then that amplitude is 0. Then in this way we can define the continuous time unit step signal. If you replace t with the n, that will be simply unit step discrete time signal, that is u of n is equals to 1 for n greater than or is equals to 0. Otherwise it will be 0 for n less than 0. In the last class I have explained this is the with respect to the graphical representation also. In this class I have discussed the one more elementary signal, that is continuous time ramp signal and the discrete time ramp signal. You should remember one point here. Ramp is nothing but it is linearly increasing amplitude signal as for the positive values of independent variable. For positive values of independent variable, amplitude is linearly varying. Here compare this signal to this signal. It is continuous with respect to the time. Amplitude and the time is continuous, but here, whereas in the discrete time, the signal is defined at discrete instant of time only. So the signal, even that is defined at the discrete instant of time, but that signal is linearly increasing with respect to the positive values of independent variable, so that it is a discrete time ramp signal and it is continuous time ramp signal. As the t value is 10, then the amplitude of the signal is also 10 and it is continuous. If the t value is infinity, and here the amplitude is also infinity. If the t value is n, amplitude also n, because r of t is equals to t only. If r of 0, that will be 0. If r of 1, that will be 1. If r of 2, that will be 2. Like that. That is keep on exponentially varying with respect to all the positive values of independent variable. And here also in discrete time signals also, as the integer value is increasing from 0 to n, then the amplitude of the signal also increases from 0 to n in linear manner, so that this type of signal is named as ramp signal. The next type of signal, that is called impulse signal. Now we are going to talk the impulse signal in continuous time as well as discrete time. So now I am going to discuss about the impulse function. Impulse function occupies an important place in the signal analysis. Impulse function has the zero amplitude everywhere except the t is equals to 0 or n is equals to 0. The amplitude is infinite at the t is equals to 0, such that area under that curve is equals to 1. That impulse signal is denoted with del of t. Just now we have completed the ramp signal. In the previous class we have completed the unit step signal, that is u of t or u of n, that is what it is, a unit step signal. And the next one is r of t is a continuous time ramp signal, and r of n is discrete time ramp signal. Now we are going to talk about the impulse signal. Impulse signal is denoted with del of t in case of continuous time. In case of discrete time, that is del of n. So here del of that impulse signal occupies the very important role in the analysis of various types of signals and systems. And here in impulse signal we can have the amplitude of the signal is 0 at all the values of t or all the values of n except t is equals to 0 or n is equals to 0. That means what? The signal can be existed at t is equals to 0 only or at n is equals to 0 only. That particular signal is named as impulse signal. That impulse signal is del of t in continuous time, it is del of n in discrete time. So that I am going to define the impulse signal in case of continuous time. In case of continuous time impulse signal, that is del of t is equals to, we know that whose amplitude is 0 where t is not equals to 0. That t is not equals to 0 means what? T may be positive or negative. That value of that signal will be 0 at only t is equals to 0. We will be having the signal amplitude that is infinity. And this is about continuous time impulse signal. If you go with the discrete time impulse signal, that is denoted with del of n. Del of n is nothing but at n is equals to 0 only we can have the signal. At n is equals to 0 we can have the signal amplitude is 1, and at n is not equals to 0, that may be positive or negative, whose value is 0. This type of signal is named as it is unit impulse signal, because the amplitude of that signal is 1 at n is equals to 0. This type of signal is named as unit impulse signal. We can see the unit impulse signal in case of discrete time signals only. Based on the mathematical representation, we can draw the continuous time impulse signal as well as discrete time impulse signal. I am going to draw the continuous time impulse signal, that is del of t, so that I can draw this is x-axis, this will be y-axis. X-axis is used to represent the time, and if it is t, and it will be minus t. Y-axis is used to represent the signal amplitude, that is del of t only. And from the definition it is clear that at t is equals to 0, at t is equals to 0, at this is t, and at t is equals to 0 only the signal amplitude is infinite, so that we can represent that signal amplitude infinity like that, so that there is no limit for this amplitude, so that we can represent like this. This is infinity. We have defined the signal is at the 0, but whereas at t not equals to 0, that means what? This part is t not equals to 0, this part is also t not equals to 0. At t not equals to 0, whose amplitude is 0, so that we can draw the signal is like this. Then this type of signal is named as it is continuous time impulse signal. It is a continuous time impulse signal, and we can draw the graphical representation of discrete time impulse signal also. I am going to draw the discrete time impulse signal by making use of the mathematical representation. We can draw the graphical representation. This is what it is, del of n for y-axis, and for the x-axis it is n and it is minus n. At n is equals to 0, at n is equals to 0 only the signal amplitude is 1, so that at n is equals to 0 you can draw the signal amplitude is 1. Signal amplitude is not here infinity, the signal amplitude is 1, and at remaining values of n is nothing but it is integer only, n is nothing but it is integer only, and integer value that is positive or negative. At n is equals to 1, 2, 3 whose amplitude is 0, and n is equals to minus 1, minus 2, minus 3 whose amplitude is also 0. That means what? If you compare this signal to this signal, at every instant of time there is a signal, and this type of signal is named as continuous time signal. And in this case, at discrete instant of time only we have the signal. Here only we have the signal, and this type of signals are named as it is a discrete time signal. It is discrete time signal. Discrete time, which type of signal? It is a impulse signal, and it is a continuous time impulse signal. And this impulse signals plays very important role. It occupies the very important role in analysis of some complex signals and the systems. And now we are going to talk about the exponential signals. Exponential signal, there are two types of exponential signal. One is real exponential signal, another one is a complex exponential signal. In real exponential signal, we can simply have the three cases, that is that either it is constant signal, and the second one is exponentially increasing signal, and third one is exponentially decaying signal, and that signals will be discussed in the next class. Thank you, students.